says recording will start soon. Okay, I think we're recording now. All right, so like I said, wanted to walk you guys through some stuff about intermolecular forces. All right, so start off with that guy. You're seeing a gecko. You're seeing him stuck to the window because intermolecular forces, which a lot of times get called IMFs, molecular M, forces F, IMFs, are all about attraction, all about things sticking together. Right? So the first thing I need to do to explain what intermolecular forces are is explain what they're not. Right? So we get a little bit of overlap here that can be tricky at times. Some substances intra, I-N-T-R-A forces, and inter, I-N-T-E-R forces have the same name. Intramolecular forces, these guys over here, are bonds. Ionic bonds, covalent bonds, metallic bonds. Right? But ionic bonds have ionic intermolecular forces. Metallic bonds have metallic intermolecular forces because the bond itself is occurring between two opposite particles. Covalent bonds have different names for their intermolecular forces. So covalent bonds are the stuff we learned about before, right? Single bonds, double bonds, triple bonds. We can draw pictures of them, but I can draw an individual covalent bond, right? So if I brought up just my paint tool here and we wanted to draw a covalent bond, I could just draw something like this, carbon dioxide. It would be C with an O on that side, an O on that side. A little bit of a review here in case you get asked to do this at some point on something, right? We'd have to start with single bonds, and then we'd go and get the electron bank, right, that I used to add up. And remember, the group on the periodic table that it lives in is what determines its valence electrons, the electrons in the bank. So an oxygen in group 16 gives me 6 valence electrons, and there's 2 of them. And a carbon in group 14 gives me 4 valence electrons. All right, and I only have 1 of those because the formula, CO2. All right, so we have 12 there plus 4 more. I have 16 valence electrons to make this picture work. Right? The single bond connections cost me 2 electrons each. So each line that connects costs you 2. So I've got 12 electrons to make that picture work. Right, and we always start from the outside in, and we're always trying to get the pictures to be 8. All right, so the line counts as 2, and it counts toward both things it connects. So this oxygen has 2, this oxygen has 2, and the carbon has 4 right now. So this oxygen needs 6 electrons. We have 12 in the bank, so we go 1, 2, 3, 4, 5, 6. He's good. Still have 6 more in the bank. This oxygen needs them. 7, 8, 9, 10, 11, 12. He's good. So my bank is empty. Then I check to see if everybody's happy. As I look, oxygen's good. It has 8. Oxygen's good. It has 8. Carbon, no good because it only has 2, 4. So whenever we come up short, what we used to do is take 2 off of one of the ones that works and then push it into a second bond into the middle. Right? Now the carbon's up to 2, 4, 6. Still not good. So we try that again. Take 2 off this guy. Push him into the middle. All right, now the oxygen 2,4,6,8, good. Oxygen 2,4,6,8, good. Carbon 2,4,6,8, good. All right, so that right there is a carbon dioxide molecule, just one. These are covalent bonds. But in intermolecular force, right, the kind you see over here, hydrogen bonding, dipole-dipole, and London dispersion, all occur between two different molecules. So if I wanted to draw an IF in a covalent substance, I'd have to draw a second molecule of it to do that. So I'd have to bring in another carbon dioxide molecule, and it's going to look the same. But an intermolecular force isn't talking about this guy, the bonds in between the C's and the O's. It's talking about the interaction of this guy with this guy. There are attraction forces between the two different molecules. And in covalent bonds, the names of those intermolecular forces are different than the names of the bonds. That is a double bond. The intermolecular force between it is one of the three you see over here to the left. It's a hydrogen bond, it's a dipole-dipole, or it's a London dispersion. So sometimes we forget that in ionic and covalent bonds, the bonds and the IFs are the same thing. But in a covalent bond, the bonds get one name and the IFs get another. All right, so that's one thing I want you guys to understand. All right, so once we have that sorted out, we're going to dive into, in particularly, these three intermolecular forces: hydrogen bonding, dipole-dipole, and London dispersion. And we're going to talk about when they happen. And obviously, like I said, we're talking about specifically covalent compounds here. If it were an ionic compound, it would have an ionic IF. And if it were a metallic bond, it would be metallic IFs. All right, so we're focusing in on those covalent IFs right now. All right, so the first one is called a hydrogen bond. Hydrogen bond occurs very specifically. It has to have hydrogen, no surprise, and it has to have electrons on an N, an O, or an F, right? A nitrogen, an oxygen, or a fluorine, right? And that creates a very strong attraction force between those covalent bonds. So the picture here is trying to show you what that's all about, but sometimes it helps if you see it drawn. So if I drew you guys the ammonia molecule, it would look like this. You have an N with a single bond to the H, a single bond to the H, single bond to the H. It has an unshared pair of electrons there. When that gets near a water molecule, which has an H connected to an O, connected to an H, and unshared pairs there and there. What we're talking about is the hydrogen of one of them being attracted to the unshared electron pair on the next molecule. Now, it's poorly named because these aren't bonds. They're not single bonds. They're not double bonds or triple bonds. It's an intermolecular force, but they call it a hydrogen bond for some reason. I mean, so I don't think when they initiated that term, it was a teacher that did it, because we would never give things that aren't bonds the name bond. All right, so this is an intermolecular force, this attraction. So you have to have a hydrogen in your formula, and you have to have an unshared pair of electrons, dots, on this guy here has to be NO or F. Right? As long as you have dots on an N, an O, or an F, and there's hydrogen present, you will have hydrogen bonding, right? Which is a pretty strong attraction force. Why is it attractive? You're getting into these goofy symbols, all right? This lowercase Greek delta that has a positive, and this lowercase Greek delta that has a negative. Right? What those are charges. All right? So I'm going to erase some things here just to get some space to work. And why do we get those charges? Well, if you remember, one of the trends that you had to learn when we were learning about the periodic table was electronegativity, the hottest kid at the dance, right? How well atoms attract electrons based on how strong their nucleus is. So what happens here is oxygen on the periodic table sits pretty darn close to fluorine. And so if I sketched you a quick section of the periodic table there. Okay, we've got helium there. We've got neon. And then we've got these three. So remember, noble gases have no electronegativity, right, because they filled the octet rule. So fluorine is the most electronegative. It attracts electrons the best. Oxygen's its next door neighbor. Nitrogen is next to it. So all three are strongly attracting electrons. What that means is in this bond right here, these electrons favor the oxygen because it's more attractive. And because the electrons are leaning toward the oxygen, that oxygen feels a little bit negative. And that's what that lowercase Greek delta means. It means partially. All right? That's a partial negative. If it were a full negative, you guys would draw it like this, like Cl -1. Like you'd give it a full charge. So think of this as like a fraction of a charge. All right, so you get partial negative because the electrons favor the oxygen, which makes the hydrogen partially positive. This happens over here as well. The nitrogen is way more attractive than the hydrogen is. So this H is partially positive because these electrons lean this way, which makes the nitrogen partially negative. So you get this partial positive of hydrogen sees the partial negative of the nitrogen, and we get opposite charge attraction, positive negative attraction. But it's not a bond, it's just an opposite charge attraction, but hydrogen is there, so that's what they call it. And so that's a hydrogen bond, really specific, right? You've got to have hydrogen, and you have to have an unshared pair on nitrogen, oxygen, or fluorine. So if I were to give you guys a couple formulas, looking at the formulas, you can tell if it's going to have hydrogen bonding for the most part. Like if I said we have H2S. Do you guys think that will have hydrogen bonding? You can just chime in, anybody. So you're asking yourself, does it have hydrogen? Right, well, we check that box. And does it have an N, an O, or an F? So you have to check both boxes to have hydrogen bonding. Is this guy going to have hydrogen bonding? Exactly. Not going to have hydrogen bonding.
No.
It has the hydrogen, but it doesn't have the N, the O, or the F So it's not going to have hydrogen bonding. Right? So the H2S, not going to happen. Right? What if we had something like Cl2O? If my formula is Cl2O, does it have hydrogen bonding? Also no, right?
No.
Why?
Because it doesn't have H.
It doesn't have the
in it.
hydrogen, so it doesn't have that. Right? So not going to have hydrogen bonding on that one. Right? What if we did something like HF? That one's going to have it, right?
Yeah.
Because we've got the hydrogen and we've got oxygen, fluorine, or nitrogen. It meets both criteria. You can say this guy is going to have hydrogen bonding. It will have H bonding. All right. And that tells us certain things because a hydrogen bond is a pretty strong IF. All right. So hydrogen bonding is your strongest intermolecular force of the covalence. And we'll recap that at the end. And you guys see these types of bonds all over the place in biology. Right? You guys learned about base pairs in biology. Right? In bio, right, thymine, right, bonds with adenine, but they aren't forming chemical bonds, right? You've got IFs, right, in here, and that's what keeps those base pairs together. The thing that creates the double helix in DNA, right, is because of hydrogen bonds between these base pairs, which are these big groups Mrs. Sherry taught you about. If we looked at another one, all right, you get CG base pairs, right, cytosines with guanines, all right, and this one's actually a stronger connection because it has a third hydrogen bond, right? The dots on this O feel the H, the dots on the N feel that H, the dots on the O feel that H. So a CG base pair is stronger than an AT base pair, and because of how DNA is created, this creates uneven shaping in the double helix, which is why you guys will learn, if you haven't, that you have major grooves and minor grooves in DNA based on what the pairings look like. All right, so we get A's with T's because of this setup. You get C's with G's with this setup. If you're talking RNA instead of DNA, it's really similar. The only difference is instead of thymine with an A, did you guys ever learn who A pairs with in RNA in Miss Sherry's class?
Is it like U or something?
U. Good. Yep, it's a U. It's a uracil. And it's a similar chemical structure. It's just not the same one, so they give it a different name. So in RNA, you get AU base pairings, but the same thing holds them together. All right, hydrogen bonds between these groupings at the end of the base pair. All right, so those are some hydrogen bonds. All right, the second one is actually identical to a hydrogen bond, except for it's weaker. So they give it a different name. All right, it's called a dipole-dipole attraction. All right, so for something to have dipole-dipole interactions, I'm saying here that the thing has to be polar. All right, and a quick recap of what makes things polar has to do with our picture again. And this is why I'm reviewing all this, because we can't talk about one without the other. All right, so if I were to draw a picture, let's say we drew NO2. All right, draw this guy up. We'll make it -1. NO2 -1. All right, we put the N in the middle, put the O's on the outside. All right, we work our electron bank. The N gives me 5. I get 2 times the 6, and a -1 there makes me add another one, another electron. All right, so we get 1 more. All All right, so we're at 12, 17, we're at 18. All right, take away 4 for your single bonds. You've got 14 left. All right, so 1, 2, 3, 4, 5, 6. He's good. 7, 8, 9, 10, 11, 12. He's good. Whenever we have extras left over, 12 made the outside guys happy. Where do our extras go? What do we do if we have leftovers?
Don't they go on the end?
Yeah, they go on the center atom, exactly. So I have 2 dots left. I'm going to put those 2 on the middle atom, and then I see if everybody's happy. And when I do that, oxygen's good. It's got 2, 4, 6, 8. 2, 4, 6, 8. The nitrogen is still not good, though. 2, 4, 6. It's a couple short, but we talked about how to fix that. What do?
Make a double bond.
Yeah, good. Take 2 off the oxygen on the outside, push it into the middle for the double bond. This guy's good. All right, so we draw this picture. All right, so you can go through the checklist. Does it have hydrogen bonding? Can't, right? So it's got no H bonding. Why doesn't it have a hydrogen bond?
There's no hydrogen.
Because there's no
hydrogen, right? So no hydrogen bonding. So the next check would be for dipole-dipole forces, all right? And a dipole moment is just that difference of charge that we talked about, right? And because oxygen is closer to fluorine than nitrogen is, we get those partial charges because these guys don't attract electrons the same. So you've got a partially negative oxygen, you've got a partially positive nitrogen, right? That is what makes something polar, is it has a dipole moment that's there. Now, there's some easier checks, right? One check to decide if you're polar, that's an automatic, is dots on the center. So if there are dots in your picture on the center atom, like this, it is definitely polar. And if it's polar, it has dipole-dipole forces. Okay. Right. The other thing is if there's no dots on the center, we did this in class, you look to see, is it an uneven pool or an even pool on the center atom, right? And that's all about who these guys are. So if it's surrounded by all the same element, it's an even pool. Even pool means nonpolar. If any of these were different, I had an oxygen and an oxygen, they're the same. But if I had made this guy a fluorine, O and F are different, that's an uneven pool, that creates a polar molecule as well. All right, so little refresher on how we know if something is polar or not. Right, first check is, are there dots on the center? If there are, yes, it's polar. You know it has a dipole-dipole moment. If it doesn't have dots on the center, if these guys are missing, right, then you look at what's around it. And if it were the original one, I have oxygen and oxygen, that would be an even pool because they're both oxygens. It would be nonpolar. But in the second setup, if I made this not be oxygen and instead it was like chlorine, O and Cl are different, it's an uneven pool, it would be polar. Okay, so some of the trickier stuff about this is I just throw around the term intermolecular force, IMF, but they come in different shapes and sizes, and the strength of them determines a lot of whether they're a solid, a liquid, or a gas. Right, so this is why we have to talk about this stuff. All right, so you've got hydrogen bonds, which is a really strong dipole moment, so they give it a different name. And then we've got a dipole-dipole, which means the substance is polar. All right, that's the middle of the road strength. All right, the last one is the easiest. It's called London dispersion. Right? It gets a couple names. They call them London dispersion. They call them van der Waals forces. So if you read something about van der Waals forces, right, those are just London dispersion. If you read about instantaneous dipoles, that's talking about London dispersion. They give it a bunch of names. But the moral of the story is simple. What types of things have London dispersion? Everything. Everything has London dispersion. So all molecules have London dispersion forces. And the reason is because electrons are in constant motion. Right? And because they're in constant motion, they can create what we call a temporary dipole moment. So if I took this picture right here and brought it over here, all right, I'm going to show you what I'm talking about with this whole temporary dipole moment. If you've got atom A and atom B, and they are the same substance, you would think like, well, they're the same. How do they have any attraction for these electrons, right, in between, right? Why would that be any different? It's not. But what happens, because don't forget, electrons are constantly moving around, right? They're in continuous motion. You might get a situation where a bunch of the electrons just happen to randomly move all onto the one side. It's kind of like I let you walk anywhere in school, and it just so happens that you guys all end up down by the gym just due to your random movement. Well, what happens is because all those electrons are down there, that area becomes partially negative, and that area becomes partially positive. And the same thing happens on the other molecule, right? We get another atom that's doing that as well, and we get that dipole attraction. But why isn't it a dipole-dipole? It's because these electrons aren't stuck here. A moment later, they may decide to walk up to Mr. V's room. And now all of a sudden, they're back to being evenly distributed, and that dipole moment goes away. So they call it a temporary dipole. They call it an instantaneous dipole because it occurs for an instant and then can go away. So it's there and then it's gone. It's there and then it's gone, right? So it's not a constant. The dipole that we just learned about on the last slide, that is permanent. That positive is permanent. The next door neighbor's negative is permanent. The attraction force is permanent. That's why it's stronger. But these guys aren't. So they're always there. That's the win. Every molecule has them, but they're very weak. All right. And that's the trade-off, right, with your intermolecular forces. All right. So you've got London dispersion, weakest, but everything has it. You've got dipole-dipole, stronger. You have to be polar. And then you've got hydrogen bonds. Right? They're the strongest of covalently bonded substances. And you have to have hydrogen attached to an N, an O, or an F. Right? So if I gave you the big spectrum of everything in terms of strength, right, you're going to see this here. You've got metallic is the strongest IF. Ionic is next, because remember, their bonds and their IFs are the same name. Then as we get into covalence, hydrogen bonding, followed by dipole-dipole, followed by London dispersion. All right, so metallic bond is the strongest IF. Ionic bond is the next strongest. And then once you get into covalent bonds, hydrogen bonding, dipole-dipole, London dispersion. All right, and you're going to see that there is a link between the intermolecular forces and all of the stuff that we talk about, melting and freezing and boiling, right? And all of that is coming to be. Tomorrow we're going to talk about properties of solids and why they are the way they are, all right? And then we're going to get into types, and you're going to find that the strength of the IFs are what control a lot of your characteristics of a solid, like why are solids fixed? Like why do they have a definite shape? We're going to get into all that. But before we did that, I just wanted to talk you guys through what are IFs again and how do we determine the IFs of a substance. And that should be enough to get you guys squared away, hopefully, on that worksheet that I sent home. All right, questions from you guys? All right, so give me a second to stop recording. And the recording will be saved in Caitlin Peterson's Google Drive. That's interesting. I would really like that to be saved in my Google Drive. So, Caitlin, I may be reaching out to you if this isn't in my Google Drive.